Okay guys, so I was asked to do a video on problems 3 through whatever on the semester review. So that's what I'm going to do. If you want me to do number 2 or number 1, just let me know, and I'll be more than happy to do it. Okay, so we're going to start with number 3, which is a related rates problem, and you're going to have several related rates problem on your exam. So make sure you know the sphere, the cone, the ladder, those kind of problems. They're going to be classical problems, not going to be anything crazy. Okay, you're not going to have shadow problems or anything. Anyway, back to number 3. So what we're given is the volume and the surface area for a sphere. Okay, and the fact that the radius of the sphere is decreasing at 0.5 inches per minute. We want to find the rate at which the volume is changing. So I always start by reading and writing down what's given to me. I know my volume formula is 4/3 pi r cubed. Chances are I'm probably not going to need this one, so I'm just going to hold off on that for a second. I know that the radius is decreasing. That's a rate of change. So dr dt is equal to -1/2 because it's decreasing. Remember, we include a negative there. Okay? We want to find the rate at which the volume is changing when the radius is 6. Okay? Easy peasy. Spheres are the easiest one. So what I'm going to start out with is, okay, I know the rate at which my radius is changing. I have a formula here with volume and radius, so the two variables that I need. The volume is changing, therefore the radius is changing, so I need the two variables. So I'm going to take that formula and I'm going to take the derivative. So if I take the derivative of the left side, I get dv dt is equal to 4 pi r squared dr dt. Don't forget, this is implicit differentiation, right? We're taking the derivative of v and r with respect to t. So we take the derivative as though we did with an x, but we have to include this dr dt, dv dt, whatever it happens to be. Okay? So, and if I threw you through a loop there, by the way, remember I'm just using the power rule here. This is just a number. So if I bring the 3 down, it's going to cancel with the 3 downstairs. So I'm left with 4 pi r subtract 1 times dr dt. So that's how I got that. This is what we're looking for. So we're going to find it when the radius is 6. So now I can plug in. So remember, never plug in until after you take the derivative, with the exception of cones, because you have to get rid of a variable there. Alright, so let's see, what is this? This is 4 times pi times 36 times -1/2. That's -18 times 4. Where's my calculator? So looks like we're going to get -72. Okay, and of course, you're going to have a multiple choice exam, but it's cubic inches per minute because that's what we're looking for. Those were the units that we wanted in cubic inches per minute. But remember, this just means this negative just means that the volume's decreasing, right? If the radius is decreasing, it makes sense that the volume would be decreasing. If the radius is increasing in the sphere, it would make sense that the volume is increasing. So this negative is just indicative of the fact that the volume is decreasing at a rate of 72 cubic inches per minute, not -72 cubic inches per minute. Okay, so be careful with that. Alright, second one. Second one, we have a cone, and they have a picture here for you. They also give you the volume formula. Now let me move this. Oopsie daisy there. And it says the container has the shape of a cone, so here it is. Okay, the height of the cone is 10. The diameter, now be careful of this, the diameter of the base here, or the opening, is 10, so that means the radius is 5. So when we work with cones, of course, we're going to be working with the radius r, so make sure you cut that in half. Now we're going to have this liquid surface. This is, I guess, water. Okay, so this is some kind of a little conic cup sitting on a shelf, and the water is evaporating. So what I know is that the volume is decreasing, right? It says water is evaporating so that the depth is changing at a rate of -3/10 centimeters per hour. Okay, A, find the volume of the water in the container. So in part A, it might seem a little tricky. They actually want you to find the volume, not the rate at which the volume is changing. That's part B. So students will get confused with that. So make sure you read very carefully. Okay, they want you to find the volume of the water when H is equal to 5, when the depth is 5. So remember, with cones, we have to do something special. The formula is a problem for us because we have the variables V, R, and H, and all of those things are changing. So the goal is to get rid of a variable, and the variable that we want to get rid of is H. Sorry, we want to get rid of R, my bad. Okay, we need the variables V and H to be left over. So before we even do anything with this, we need to use similar right triangles. So remember, R is to H as 5 is to 10. So that implies that R is equal to 1/2 H. Okay, and I want to do this because I'm going to replace this in this formula to get rid of R. So everything's in terms of H. So we're going to do that and clean that up. So volume is equal to pi over 3, so 1/3 pi is pi over 3, times 1/2 H squared times H. If I clean that up a little bit more, I'm going to have pi over 3 times 1/4 H squared times H. And cleaning it up, a little bit more, this is going to give us pi over 12 H cubed. Right? H squared times H is H cubed. Now, I want the volume when H is 5, so that implies that the volume is going to be pi over 12 times 5 cubed, which is 125 pi over 12 cubic centimeters. Okay? We just wanted the volume. No derivative to take there. Now in B, we do want the derivative. In part B, we want to find the rate at which the volume is changing when H is 5. Okay, well, I have the compacted or simplified volume formula, so let's take the derivative of that thing. On the left, we get dV dt is equal to, now if I bring the 3 down, this is going to become pi over 4. It's going to cancel with a factor of 3 in the bottom. So I'm going to have pi over 4 H squared dH dt. Alright, and now here's the thing. I was given up here, I don't want to lose sight of the fact because you may be thinking, oh my gosh, I don't know what dH dt is. Yes, you do. If you look up here, we know that the depth was changing at a constant rate of -3/10. So I know what H is, it's 5. I know what this is, so now I can plug in and find my rate of change for my volume. So I'm going to plug a 5 in there and a -3 over 10 for that. And let's see, this is going to become 25 pi over 4 times -3 over 10. And let's see, 5 goes in here twice, and 5 goes in here 5 times. So it looks like it's going to be -15 pi over 8 cubic centimeters per hour. And again, for the semester exam, you're not going to have to worry about the units because it's going to be multiple choice. Okay, let's go on to the next one. That'll be in the next video.